Now welcome back. This is lecture 21. So let's continue our discussion on narrowband low noise amplifiers. Right. In the last lecture, we saw how to not use noisy elements, but yet be able to generate a real impedance, right, and use it for matching. And the supposed benefit is, if I am not using an explicit resistor or a transistor to get the final matching, then I should be able to benefit from low noise figure, right? That's the supposed assumption. And with that in mind, what we saw was we came up with this architecture. It's a low noise amplifier where we are only concentrating on matching right now, with an inductor at the source, and this is, let's say, the CGS capacitance associated with the device anyhow. So this is L. Let me call this LS for the time being, because this is an inductor that is connected to the source. And we saw that for this configuration, the effective impedance Zin was j omega Ls, that is the source impedance, then 1 by j omega CGS, that is the impedance provided by the capacitor. It's no surprise that the CGS and Ls are effectively in series, so they should also appear as is. But there is an interestingly extra term. That term was essentially omega t times Ls, right? And we saw that if at frequency where L and C can resonate out, right? So at omega equal to omega naught is equal to 1 by under root Ls CGS, your Zin at omega naught effectively becomes real omega t times Ls, right? And if I set it to Rs, right, if I set it to Rs, then we have an impedance which has a real part of Rs, right? And hence we should be able to provide a perfect in-band match, a perfect input match, without using any additional resistive elements, right? Now note that you should turn around at this point of time and say that, okay, hey, what about at frequencies which are deviating from omega naught? Sure. So when you are deviating from omega equal to omega naught, this relationship strictly doesn't hold, right? But note that this whatever we have, right, is j omega Ls plus 1 by j omega CGS. This is essentially 1 minus omega square L S CGS by j omega CGS, right? So if you are at omega equal to 1 over omega square equal to 1 over Ls CGS, then sure it is 0, but moment you deviate, you are still getting an imaginary term, but that imaginary term can be, it will not suddenly blow up to a very large value, right? So it can still be much smaller than that 50 ohm mark, right? Maybe 1 ohm, maybe 2 ohm, I don't know. I mean, so depending upon how far you are away from omega equal to omega naught, you are going to get some imaginary term. But if you go back to the expressions for reflection coefficients, and if you go back and find out what is the effective S11 bandwidth for which I still get S11 of less than 10 dB, minus 10 dB, then you will see that it's not like matching at a single frequency, but it is also matching at a range of frequencies. So do it yourself, right? So find the range of omega around omega naught for which S11 is less than minus 10 dB, right? So, so do it yourself, and then uh, hopefully you'll be able to. We can discuss it later, or maybe you'll. This can be one of the upcoming assignments, right? So do it yourself. Okay, fine. I hope that we understand from whatever discussion we had till now that uh, granted that this is a single frequency solution, but there is a hope that it is it will. I mean, we understand the fact that this solution is not going to just go for a toss moment to go slightly away from omega naught, right? So as long as this imaginary part is much lesser than the supposed real part, then I can basically say that my frequency is all right. Okay, my match is all right. Okay, fine. So that is and another important part is note that the real part is independent of omega, right? So even if you deviate from omega equal to omega naught, only the imaginary part changes, the real part does not really change. Okay, so that's to our benefit. So now so having said, I mean, this is where we stopped in the previous lecture. So in this lecture, what we are going to do, we are going to find out the effective what are the typical properties of a LNA that we need to be aware of. One is matching, the second is gain, and the third is noise figure. At least, right? There are many more things. These are the things we are till now we understand that we have to take care. So so now that we understand that matching is done, so let's try to find out the gain. Before trying to find out the gain, let me address an issue that generally happens with this particular topology. Is that note that in this case, what is happening in this case, who is setting the resonance frequency? The resonance frequency is getting set by the parasitic CGS and LS, right? And LS is also setting your match, right? So LS is setting both the real part and also the frequency at which you are trying to resonate, right? So now let's say you want this LS to set the real part, but you maybe the same LNA you would like to use it for matching at a slightly different frequency, right? So what are you going to do? So you cannot change LS, because if you change LS, your matching will go for a toss. You cannot change CGS, because if you change CGS, your omega t will change, right? One might say I can change both GM and CGS, right? So that omega t doesn't change, but CGS changes. But if you want to increase CGS, then you have to increase GM also. So which means you end up burning more power. But if you want to reduce CGS, you cannot even do that, right? So because you are probably but yeah, I mean, that's typically not the problem. The major problem is if you want to increase CGS, you also need to increase GM, so you end up burning more power. Now, without getting into all these design constraints, the key problem here is that the single variable LS is setting both the real part and also the resonant frequency. Now, in any design, you would like to have design handles which are responsible for setting one particular property, not everything else, right? If one design handle sets 3 or 4 parameters, then it becomes very difficult to optimize anything. Ideally, in this context, we would like to ensure that the LS only plays the major part in setting the real part of the impedance, that is setting matching, giving us matching. But we would like to free off LS from the responsibility of setting the resonant frequency also. So what can we do? So obviously, if we do not want to change LS, but I want to change the resonant frequency and I don't want to charge CGS, what else can I do? So an option is maybe we see that we have not yet touched anything in series with this contraption, right? So how were we setting up the Z-in? We were setting up the Z-in by, we were evaluating Z-in by putting a test voltage, and this was our contraption. right? Right? So this is whatever I test we get, then V test over I test was our Zin. And we understand that the resonance is happening because of this L and C are in series. If I want to shift the resonant frequency without affecting that term omega t times Ls, what can we do? The simplest thing that we can do is probably put an inductance here, and let's say I call this Lg. Now note that will this Lg affect the real part? Clearly no, because even if I have this Lg and I look with this Lg, what is the equivalent looking in impedance? So the equivalent looking in impedance becomes V test Lg, then this CGS, then this Ls, and then this omega t times Ls, right? So this is CGS. So now previously the CGS was resonating with Ls. Now I can size the Lg in such a way that the combination of Lg plus Ls resonates with CGS. So I basically then free of Ls from setting the resonant frequency alone, right? Ls times omega t can set the 50 ohm match, and the combination of Lg and Lg can be used to move the center frequency around, right? So essentially use Lg to move the center frequency and use omega TLS to match, right? So that is a easy hack that often can be done, right? Okay, fine. So now that is out of the way. So let's concentrate on the gain that we get from this type of LNA. Now, in order to get the gain, what do we need? We need to find a Thevenin's equivalent, and most importantly, we need to find the effective transconductance or the short circuit current, right? Just like we do in any common source amplifier or any analog circuit analog circuit analysis, we try to find the Norton equivalent, and then once we find the Norton equivalent, we get the gain, right? So essentially we have to find out the short circuit current. So in order to do that, what should we do? So again, so let's say I have a V in, and I am not showing the effect of Lg in this analysis. We assume that things have been resonated, right? And things have been resonated, the analysis doesn't really change, because ultimately the Lg will go off in your analysis, right? So by the way, I should make this disclaimer: all analyses are being made or being done at resonance from now for this LNA, right? So I mean, because we understand that things we will be using this LNA at the resonance, then there's no point in dealing with these extra pesky terms and later setting it to 0. I would rather not have them in the first place, right? Okay, fine. So let's go ahead with that. So the circuit does not change just because I am doing resonance, so circuit remains the same. What am I interested in? I'm interested in finding out the short circuit current, because if I find out the short circuit current, that will effectively go into the load, and that will give me the output voltage. So essentially I'm trying to find out the effective GM, right? In a common source amplifier, the effective GM is the GM of the transistor itself, but clearly in this case it cannot be, because we have this inductor which is connected at the source. Okay, fine. So how should I go about doing it? Under matching condition, let's assume further, right? We will assume the input is matched, right? So under matching condition, what is the current that will flow in? So obviously the impedance is Rs, right? The impedance is whatever Rs you want it to be. So the current is V in over Rs, right? Okay. So what is this voltage? What is VGS? Your VGS, I should write capital, because I think I have been guilty of using small VGS while I was using even Laplace or phasors. But I mean, since we are all doing everything in phasors, no harm done. But strictly speaking, we should be using capital V for these analysis. Okay, fine. So you have VGS is essentially V in over RS times 1 by j omega CGS, right? And what is ISC? It's basically GM times VGS. So ISC is GM times VGS, which is GM by j omega CGS V in by RS, which means that your ISC by V in, which is effectively the transconductance of this contraption, is GM by j omega CGS, which is omega t by omega by RS. Or in other words, I can effectively say that the mod of this ISC by V in, which is the mod of GM effective, is omega t by omega times 1 over RS, right? So as far as this stuff is concerned, this network is concerned, what is it telling us? This is effectively telling us that if I apply a V test here and I have a transconductor, this is a negative sign, if I have a transconductor GM effective, so this GM effective equal to omega t by omega by 1 over RS, right? Ideally it should be J times, and I say that there is an input impedance of omega t times Ls is equal to Rs, right? So this effectively models the LNA, right? So this is effectively, so effective short circuit current model of the narrow band or of the LNA. I should not say generic narrow band for this particular LNA, right? So I mean, just like you in case of a common source amplifier, in case of a common source amplifier, if I have to distinguish this with a common source amplifier, so then in a common source amplifier, this is effectively the GM of the common source amplifier, and at the input, if you have to put for matching, you have to put an explicit RS. In this case, this RS gives us noise, but in the narrowband LNA case, that effective RS does not give us noise. And in this case, in the common source amplifier configuration, this is for common source amp. In the common source kind of configurations, the effective GM is basically the GM of the transconductor, right, which is GM of the transistor. But in our case, the effective GM is omega t over omega times 1 over RS. Note that this is under matched condition and at resonance and so on. The good thing about a common source amplifier is that it is a wideband match, right? It's not, the match is kind of not frequency dependent if you are well below that cutoff frequency of CGS and RY2, right? But in case of a narrowband LNA, obviously you have a frequency limitation. Now, in case of a narrowband LNA, if you want to increase the GM effective, or rather if you want to increase the gain, right, what are you going to do? Ultimately, there is a load that is connected to the LNA, right? So ultimately there will be a load that is connected to the LNA. What I mean by that is that in principle you are going to have something connected, right? Here you are going to maybe have an inductor or some ZL. Let me just write a ZL, some load, and you'll be biasing through some voltage supply that will be connected. So if you have that load in a small signal model, what are you going to do? You are going to basically replace this short with a ZL, and you tap the voltage here and you get whatever you get, right? But the key thing is that given for a fixed load, the only way to increase the gain of the LNA is by increasing GM effective. And you see that GM effective is, under all the constraints that has been set up, is also proportional to omega t by omega, right? Which essentially means that if you have to increase again you have to ensure that you bias your transistor with the maximum omega t as possible. As you can see, that there's a lot of benefit of biasing your transistor for the maximum omega t that you can, right? So we have been harping about this right from the beginning of the course. Okay, fine. So this is as far as biasing that your narrow band LNA for getting high gain and for getting matching, right? So the next part is to see what impact does all these things have on the noise, right? Because ultimately we wanted to do all these things because we wanted to reduce noise figure. Okay, so that's what we are going to do next. So to evaluate noise, what we do the usual thing. We we introduce all the noise sources one by one, find out their total contribution to the input or the output or any particular point. In this case, we'll be concentrating on the output, and then find out the noise contribution due to the source and noise contribution due to everything else, noise contribution due to everything, and then divide the one from another, and the ratio is essentially our noise figure, right, or noise factor. So that's what we'll do. Again we'll do everything under the condition that it is input matched and we are working at resonance, right? So that helps ease the algebra a lot. And also, that is what we ultimately want, because we want the LNA to be working at resonance under matching condition for the band of interest. Okay, so let's start off. So we have this RS. Again, we are interested in the short circuit current, so I will neglect the load, which I assume maybe is an inductor or is a non-resistive element, right? Later on in the course, we'll also introduce resistances and the effect of losses. At that time, we'll maybe revisit the effect of noise. But for the time being, let's only consider the effect of lossy elements, which are RS and IN, right? Okay. So this is my noise source IN. What I am interested in is finding out what is IN out. What is the power spectral density of IN out? Okay. So few things. So if that is IN out, which means IN out is coming from here, which means I know that IN out has to go into that junction. So this has to be IN out. That much I know for sure. Okay. So if that is IN out, what is the noise current through the GM, right? So this note that the transistor is essentially a voltage control current source, which is GM VGS. So if I can find out what is the current flowing through this current source, then I will be able to find out what is the VGS, and from VGS I'll be able to find out the voltage, the current through the capacitor CGS, right? So that's how we are thinking. So what is this current? This current is essentially, if I call this IGM noise, right? The part of the noise current from IN that goes through the channel is essentially, so IGM noise plus IN out is equal to IN go back to black color, which means IGM noise is IN minus IN out. Okay, okay, fine. So let's deal with this IGM noise, and then we'll take one step at a time. So if that is a one IGM noise, I know that this voltage, right? This voltage is IGM noise by GM, correct? Okay. If that is IGMN by GM, what is the current through the capacitor, is basically J omega C times this voltage, which means this current is IGMN by GM times J omega CGS, correct? I know that this voltage is 0, which means this voltage is how much? That voltage is this current times RS negative of that, right? So I know that VG, is equal to minus RS times IGMN by GM times J omega CGS. Okay. Okay. So which means, what is this voltage? What is Vs? So essentially Vs is this Vg minus whatever the current, Vg minus that Vgs, right? So Vg, this is essentially your Vs, and your Vs is minus Rs J omega CGS over Gm minus IGMN over Gm. Fine. Okay. So I can also figure out Vs from another direction. That is, I know that this current is IN out, correct? And I know that this current is IGMN by GM times J omega CGS. So I can figure out this current. So IL, I call this IL. So IL is basically IN out minus IGMN by GM J omega CGS, correct? So what is Vs from this direction? So your Vs is essentially 0 minus this IL times J omega Ls, right? So basically minus J omega Ls times IL, right? So I will equate this and this. So equating A and B, what do I get? What we get, minus Rs J omega CGS over Gm minus IGMN over Gm is equal to minus J omega Ls IL, where IL is IN out, minus IGMN over Gm times J omega CGS. So I will get all the GM and IGMN together. I think I missed something. Here I missed IGMN, right? So this should be IGMN. Minus IGMN. Okay. So you see, IGMN over GM is common for many of these terms. So by the way, I'll make everything plus. So which means that IGMN by GM is J omega CGS RS plus 1, and I get plus omega squared CGS LS, right? So we have a minus, and J becomes another minus, so it's plus. If I take it on the left hand side, this becomes minus, which is equal to J omega LS times IN out. Now at resonance, this cancels off. So at resonance, this goes 0. Okay, which means that I get IGMN by GM equal to, so or rather IGMN by GM times J omega CGS RS is J omega LS IN out. So this also goes off. So now I can replace the IGMN. What was IGMN? Is IN minus IN out. So this becomes IN minus IN out over GM. And this GM over CGS is essentially omega T. So I will keep it as omega T times RS is equal to LS IN out, right? So this becomes IN minus IN out is omega T LS over RS times IN out. Now note that omega T times LS is equal to RS, right? So this is equal to 1 under matching condition. So essentially you get IN out is IN over 2, which means that your SNI out, this is due to GM noise, is KT gamma GM, right? Okay, so the major part is done. What else we need to do? We need to also find out what is the noise due to RS, correct? So that is easy because we essentially know the impedances and everything. So but still let's go about doing it. So this is Vn, due to RS, right? So if this is Vn under matched condition, this is Vn over 2, right? And I know the transfer function from Vn over 2 to In out, which is GM effective. So I know that In out is, so this is again at under matched condition. So your In out is Vn over 2 times GM effective. And what is GM effective? This is Vn over 2 times GM effective is omega T over omega times 1 over Rs, right? That's what it was, right? Yeah. So this is omega T over omega times 1 over Rs, which means that this is In out due to Rs, which means that Sn out due to Rs, that is due to source, is omega T by omega whole squared times 1 by Rs squared times 4k, sorry, 4 goes off because 1 over 4 will come. So you'll get KT Rs, right? So what is noise factor? Noise factor is basically the total noise divided by noise due to source, and total noise also has a noise due to source. So I get 1 plus that additional noise, but the noise due to source. Additional noise is this, that is KT gamma GM by noise due to source, which is omega T by omega whole squared times 1 over Rs times Kt. So this goes off. So I get a noise factor of 1 plus gamma omega by omega t whole square times Gm Rs. Right? So note that this is 1 plus, this is not 2 plus. Right? In a common source amplifier, when we were enforcing a match using a resistor, I was getting 2 plus some additional term, and even if I could have gotten that additional term to 0, the minimum noise figure that it could have gotten was 3 dB. But in this particular configuration, I get 1 plus some additional term, right? And so if I can get the additional noise term to go to 0 or much lesser than 1, my noise figure can be as low as 0 dB, closer to 0 dB, right? So as you can see that this is this probably is a much better solution with respect to getting the sensitivity of a receiver lower by at least 3 dB. Okay, and again you see that what is the impact of omega t here. You would want to bias your transistor to ensure that you are biasing it at the maximum omega t as possible. That is, you would like to have omega over omega t to be very small, right? Before we move on, there are a couple more things that probably I should mention. The things that I have neglected till now is the following. We understand that when we have this Rs and we have the transistor, there is also an additional resistance Rg, and the Rg can appear because of not only the trace, the polysilicon trace, which we can reduce, but also because of the effective channel noise, that correlated channel noise, and that contributes to the noise at the input, right? So this Rg, you can have some sort of Rg, and then you have your LNA, right? So if I have an Rg in series with Rs, how will the noise factor get affected? So we'll do the same calculations again, and the transfer function due to Rg and the transfer function due to Rs is identical. So essentially what we are going to get is this, whatever f I get, I'm going to get that f, but plus an additional term, right? So the effective noise figure that I'm going to get is 1 plus gamma omega by omega t whole square times Gm times Rs plus an additional term. The noise due to Rg will be, the expression should be the same as noise due to Rs, right? Just that I will have instead of this Rg, I'm going to have Rs, right? Or instead of that Rs, I'm going to have Rg, and eventually I'm going to divide by this term. So essentially I will end up having an additional term, Rg over Rs, correct? So now how do you go about? Now note that this Rg, so if we neglect the channel noise, then Rg is independent of Gm, right? And if that is the case, right, so in that case your f becomes 1, f remains Rg over Rs plus gamma omega by omega t whole square Gm times Rs. So if, let's say, you are operating at omega close to omega t, right? So if Rg by Rs is not very less than gamma omega by omega t whole square times Gm times Rs, then obviously you cannot neglect Rg over Rs, right? So in that case, some sort of optimization can be done. And how do you optimize that? You essentially write out this and say that I would like to, can I find out a way of, is there a optima as far as the source resistance is concerned, right, for which f I can get an f minima, right? So essentially what I'm asking is, question is, is there an optimum RS for which f equal to some f min? That's the question I'm asking. And now you might ask that why, how can we now suddenly say that RS can be changed? Hold on for 2 minutes. So I will comment on what designers tend to do when push comes to shove and we have to do something with RS, right? But let's for the timing assume that if it can be changed, is there something that we can do? So clearly, if RS goes to 0, tends to 0, the last term is we benefit from the last term, but Rg over Rs will tend to increase. But if Rs tends to go to infinity, right, clearly Rg over Rs goes to 0, but the last term tends to dominate, right? So you essentially do the age old thing, you set del f del Rs to 0, and if you do that and you find out the Rs optima, your Rs optima will be under the condition when these two terms will be equal, that is our Rg by Rs will be gamma omega by omega t whole square GMRS, which means that your Rs opt is equal to, so you get omega t by omega under root Rg by gamma, right? So when you get this optimum RS, whatever the value might be, you get a minimum noise figure. Now the question that you might ask is that, hey, how come now I am suddenly tampering with RS? So the thing that you need to understand from that perspective is, what is RS? RS is not only the source resistance, but when I have an LNA or any block for that matter, any LTI block, RS is the equivalent resistance looking towards the source, right? So I have the source, I have Rs, I have an equivalent resistance, whatever is a Thevenin equivalent resistance looking into the source, which is Rs. Now can I put something in this, can I put something here so that this equivalent resistance can be brought down? Now obviously we can. I mean, if you recall the discussion that we had long back about about the use of transformers, right? So I can put a transformer for that matter. So let's say I put a transformer, and I say that the turns ratio is n:1, right? Which means that the equivalent impedance that I see now is Rs over n squared, right? So if required, I can modify the effect of Rs. I mean, I can increase or decrease it based on our requirement. Okay, so there is a handle, but this handle does not come for free, because as it turns out, we'll see in some subsequent lectures, all these transformers, inductors, capacitors, especially inductors, they tend to be lossy, right? So, which means that they come with their associated real resistances, which also will tend to contribute to noise. So they will also tend to add up to Rg. So this is a fine balance. So that's what the designer's job starts, to understand what are the total sources of noise and what is the fine balance that I need to, or the tightrope that I need to when I am trying to minimize noise, right? Okay. So a quick recap of what we did today. We essentially started off from the previous lecture, and what I wanted you to do is to find out for this narrowband LNA, do a DIY exercise, that what is the range of omega around omega LO for which I get a match of S11 mod of S11 to be less than minus 10 dB. It will be a good exercise. Then we saw that how we can, the issue that we found was the LS was having too many things to do. It was not only setting the 50 ohm match, but it was also setting the resonant frequency, and that becomes a problem if I do not want the resonant frequency to be fixed. I want it to be going back and forth based on my separate requirements. So we introduced another design variable, which is LG. Then we found out what is the kind of effective transconductance which is essentially necessary for us to ensure that we get sufficient gain. So GM effective, as it turns out, under matching condition is proportional to omega t over omega, right? So again, surprise, surprise, would like to increase omega t over omega, right? Which means bias your transistor for maximum omega t. Then we went ahead and did a brute force analysis of the noise figure, and as it turns out, after you do all the math, your noise figure is basically, it's not 2 plus something, it's 1 plus something, and whatever the something is can be minimized. Then we introduce some non-idealities also, which some practical circuit designers face, which means that you will not only have the noise sources that I analyzed for, there will be some excess noise sources, and I gave you a framework as to how to go about solving those under different conditions. Now note that these optima condition that we found out did not necessarily be true if RG, if you consider the effect of channel noise into RG, because in that case the channel noise is also a function of GM. You can do the math and you will come out with a different optima. But the key point to note is that through this noise analysis and through this example of this prototype LNA, we could at least have an idea about how to go about designing something for low noise requirement. At least the key thing for any designer's life is to understand what are the questions to ask, right? So I hope that through these few lectures on LNA, we could address what are the questions to be asked as far as designing an LNA is concerned. Having said that, we have not yet touched upon an important aspect, which is distortion. Right? Till now we have essentially focused on gain, noise and matching, right? Now before I end this particular discussion on noise of this low noise amplifier, there is a name for this low noise amplifier which has a resistance connected to the source. This was essentially source degenerated low LNA. This is called a source degenerated, right? If somebody tells you that you know how to design a source degenerated LNA, this is typically what one is referring to. Okay, fine, we'll stop here.